Good morning, good evening, good afternoon. Welcome back for Chapter 8. In this chapter, we're going to be talking about the environment in which reactions happen. And when we think about a reaction happening, at the heart of a reaction is a collision. Okay? I've got to slam molecules or atoms together to get old bonds to break and new bonds to form. Even if I have two pure elements like oxygen come in a molecular form. It's O2. So to get oxygen to combine with other things, I have to break the bond of oxygen with oxygen. So we've got to have a slam, okay? So what we have to think about then is what kind of environment do our reactants have to be in to get a collision? Okay, what kind of states do my reactants have to be in? Turns out that at least one of the reactants needs to be mobile. That means in some kind of phase where it can move. So that means gas phase, that means liquid phase, that means aqueous phase. If I just put two solids together, you're not going to get a whole lot of slamming and reacting going on. Okay? Now, what we're going to see then when we look at reactions is a lot of reactions happen in an aqueous environment. That means that the reactants are dissolved up in water. We then need to be able to keep track of our number of reactant particles in solution. Now let's remind ourselves about what a solution is. A solution is a homogeneous mixture. Means mixing at the atomic level. The components in the solution are classified as either solvent or solute. Okay? Solvent, that's the component usually present in larger amounts and does not change phase. So if I have an aqueous solution, water is my solvent, and it's our most common solvent. Solutes, these are the component or components present in smaller amounts and may change phase. So if I were to mix water and table sugar, water is a liquid to begin with, table sugar is a solid to begin with, the mixture is a liquid. So the sugar was my solute because it changed from a solid phase into a mixture that is a liquid. It became dissolved. So we talk about the solute dissolving up in the solvent. So, how do we keep track of amounts of solutes in a given amount of solution? Well, we're going to use concentration. Here, when we use the word concentration, we're not talking about thinking real hard about something, okay? Concentration for us in chemistry means the amount of a component in a given amount of solution or solvent. For example, I could say that I have 5 grams of sodium chloride in 100 milliliters of solution. Or I could say that I had 1 milligram of something in 1 milliliter of solution. Grams per milliliter or milligrams per milliliter as ways to express concentration are common to see in geology. You'll see it in biology some. You'll see it in medicine. It's really not a very convenient way to express concentration for a chemist because we're looking at chemical reactions and we ultimately want to be able to do stoichiometry. And stoichiometry centers around that mole ratio, the mole to mole relationship within a balanced chemical equation. So let's look at how a chemist expresses concentration. The most common way to express concentration for a chemist is molarity. Now, the symbol for molarity is a capital M, but notice this one's got nice straight legs. Molar mass had the curly Q feet and the kind of curly Q capital M. I know it's nitpicky, but that's what we've got to do to make our symbols work. Molarity is moles of solute over volume of the solution in terms of liters. Okay? So let's try a couple of problems. Our problem reads, what is the molarity of a sodium chloride solution made by dissolving 3.56 grams of sodium chloride in 500 milliliters of water? So let's take this problem on. So our solute here is the sodium chloride. Notice it said 3.56 grams of sodium chloride in 500 milliliters of water. So we've got 3.56 grams of NaCl. Our solute, because molarity is equal to moles of solute over volume of solution in terms of liters, then my solute needs to be converted from grams to moles. So I'm going to need the molar mass. So 22.98 plus 35.45, 1 mole of NaCl has a mass of 58.43 grams. So 3.56 divided by 58.43 gives me 0.0609 moles of NaCl. Okay? Now my volume of my solution is given to me as 500 milliliters. I should have put a decimal point in there. We're going to assume there's a decimal point there. I need it in terms of liters to go into the molarity. For every 1 liter, there is 1,000 milliliters. So that's 0.500 liters. Our molarity then is going to be 0.0609 moles of NaCl for every 0.500 liters. So our molarity here is equal to 0.122, and I could write moles of NaCl over liters. You will also sometimes see it written as concentration equals 0.122 and the big M. The big M then stands for moles over liters. Okay? Now, says for us to look at practice problem 8.1. So let me see if I can get the document cam in this room to work with me. If not, I will read it to you. So how do I switch to document cam? Well, you know what? I don't see where to do that. So we'll just have to go with me reading. Okay, if I look at problem 8.1, okay, it's on page 321 in your textbook, so you guys ought to be able to read it. It says calculate the molarity of the solution formed by adding 45.4 grams of NaOH to a flask and dissolving it with water to create a total volume of 2.50 liters. Okay, so let me get this erased. So this is 8.1, page 321. And we're asked molarity. And we're given that we have 45.4 grams of sodium nitrate, and our volume is going to be 2.50 liters. So our step one is to go from grams of sodium nitrate to moles of sodium nitrate. I'm going to need the molar mass, so 22.98 plus 14.067 plus 3 times 15.9994. So 1 mole of sodium nitrate has a mass of 85.0452 grams. Okay? So 45.4 grams of sodium nitrate, 1 mole of sodium nitrate for every 85.0452 grams of sodium nitrate. So 45.4 divided by 85.0452, that gives me 0.534 moles of sodium nitrate. And our step 2 is just to calculate molarity. The molarity is going to be 0.534 moles of sodium nitrate over 2.50 liters. This time the volume was already given to us in the right unit, so I didn't have to do a step where I converted my volume unit. So 0.534 divided by 2.50 gives me a molarity of 0.214 moles of sodium nitrate per liter of solution. Okay? There are variations on this theme of concentration that we can see when we're problem solving. Namely, sometimes we need to go back the other way. Let's say we know the volume of the solution we want to make, and we know the concentration of the solution we need to make, and we need to know how many grams of solute we need to measure out. Okay? So, let's say we had the problem, how many grams of magnesium bromide would I need to weigh out to make 250 milliliters of a 0.45 molar sodium bromide solution? So I'm going to have to calculate grams of magnesium bromide. So let's look at rearranging the molarity equation. If molarity equals moles divided by volume in liters, then if I multiply both sides by volume, what we get is the moles of solute equals molarity times the volume. And then once we have the moles of solute, we can calculate grams of solute. So let's do this problem with the magnesium bromide. Okay? clear the board again. All right, so we're asked grams of magnesium bromide. Okay, we're given that we have a 0.45 molar magnesium bromide solution, and we want 250 milliliters. Well, actually, I just wrote 250. All right, now, step one is I'm going to go from 250 milliliters to a volume in liters. So 250 milliliters, 1 liter for every 1,000 milliliters, that's 0.250 liters. My step 2 here is I'm going to calculate moles of solute. Okay, so moles of solute is going to equal molarity times volume. So the molarity is 0.45 molar, and our volume is 0.250 liters. We do the math. 0.45 times 0.250, I get 0.113. Well, actually, I limited myself to 2 significant figures, so 0.11 moles of magnesium bromide. Okay, we're almost there. We're to our step 3. I'm going to go from moles of magnesium bromide to grams of magnesium bromide. We're going to need molar mass. Now, I don't have the atomic mass of bromine memorized, so 79.90 times 2 plus magnesium, which is 24.31. Okay, so 1 mole of magnesium bromide has a mass of 184.11 grams. Now, finishing this off then, I'm going to take 0.11 moles of magnesium bromide times 184.11 grams magnesium bromide for every 1 mole of magnesium bromide. Moles and moles divide out. So 0.11 times 184.11 gives me 20 grams. Now notice I put the decimal point in there because we've got 2 significant figures. I could also write this as 2.0 times 10 to the 1 grams of magnesium bromide, so it's very clear how many significant figures I have. Let's let that sit there for a second so you can look at the problem. Okay, you can look at practice problem 8.2 on page 322 in the book to give you another example to do. Now, once we have something in solution, we have a very convenient way to measure out moles of material, because I can measure out things by measuring volume. Okay? And it's easier to carry around a graduated cylinder or a pipette than it is to carry around a $400 balance. Okay, you don't need power for a burette or a pipette or a graduated cylinder. We might face a question like the following. This is very, 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 very common. How much of a 0.50 molar HCl solution do you need to measure out to have 0.2 moles of HCl? Well, rearranging the molarity equation again, notice this time we're given molarity and we're given moles and we're asked volume. So rearranging the molarity equation, we get volume is equal to moles divided by molarity. So let's take on this problem. Okay, so you guys look at the problem there. We're going to figure out what volume of a solution I need to measure out to have a specific number of moles of solute. So I'm asked volume, and we were given that we had a 0.20 molar HCl solution and that we needed 0.50 moles of HCl. So if I just use the rearrangement of the equation, volume is going to equal moles divided by molarity. The volume then is going to be 0.50 moles of HCl over 0.20 molar solution. Remember that big M stands for moles over liters. So the moles and moles are going to divide out. We're going to be left in a unit of liters. 0.50 divided by 0.20 gives us 2.5 liters. Okay? So, not a bad problem. That is very common in a lab setting. So, look at that for a second. Make sure you got it all down. Okay? All right. Another common practice that we're going to see when dealing with solutions, okay, is the dilution of a solution. I love that, it rhymes. Dilution of a solution. Dilution is a process of making a less concentrated solution from a more concentrated solution by adding extra solvent. Okay? Dilutions happen when I mix two solutions together. Dilutions happen when I pour in pure solvent into an already made solution and change the volume. But anytime you increase the volume, you do a dilution, you decrease the concentration. The nice thing about a dilution is that the moles of solute haven't changed, just the volume of the solution. We know that molarity times volume equals moles of solute. So when I put them in a bigger volume, a bigger container, it doesn't change the number of moles of solute. Okay? So molarity initial times volume initial has to equal molarity final times volume final. The nice thing about a dilution problem is that it doesn't matter what the volume unit is. It doesn't have to be liters. As long as the volume unit matches, we're okay. Now let me show you an example of a dilution problem. Let's see. Let's say we had 50 milliliters of a 1.6 molar HCl solution. And we dilute to a volume of 150 milliliters. What is the new concentration? Well, our molarity initially is 1.6 molar. Our volume initially is 50 milliliters. Our volume final is 150 milliliters. It's my molarity final that's in question. So we're just going to plug in. Molarity initial, volume initial has to equal molarity final, volume final. Our molarity initial is 1.6 molar. Volume initial was 50 milliliters. That has to equal molarity final times 150 milliliters. So 1.6 times 50 divided by 150 says that our molarity final is 0.53. Not too bad, right? We're going to use dilution quite a bit second semester when we're doing lab. I'll refresh your memory second semester about it, don't worry. All right, continuing on here in chapter 8. We're going to look at using solutions in a reaction stoichiometry problem, okay? So a solution stoichiometry problem, we can use a graduated cylinder to measure out specific moles of materials, and it'll allow us to predict how many moles of product or how many grams of product we can get in a convenient way on a bench top. So here's the kind of general pattern. We can go from moles of material A to volume of material A using molarity to get moles of material A. Then using the balanced chemical equation, we could go from moles of material A to moles of material B. And then if we have a molarity of a solution, we could say how much volume of a solution B we would need to react it with. Okay, we could go from volume of A to moles of A to moles of B to grams of B. Why did I put that one in there twice? I'm sorry guys, I put this one in here twice. I'm not quite sure why I did that. Oh, it's because I started out with mass of A to moles of A to volume, moles of B to volume of B. Okay, so those are three patterns to find. So if you're given concentration and a volume of a solution 1, and you're asked volume of a solution 2 that you're given a concentration of, you use pattern 1. If you're given volume of a material A and its concentration, and you're asked mass of a material B, you use our second option. And here in the middle, last, if you're given mass of an A and you want to know how much of a solution that contains B you need to react it with, you're going to use the bottom one. Okay, so we're going to look at a practice problem, and then we're kind of be done with stoichiometry. So we're going to look at problem 8.4. Okay, so let me get to 8.4. It's on page 325 in your textbook. And let's figure out which pattern we're going to be working from. Now, well, Actually, the follow-up problem is on 326. So flip over to 326. We look at the problem. It says, what volume in milliliters of a 0.150 molar HCl solution will completely react with 35 milliliters of a 0.70 milliliter 0.108 molar sodium carbonate solution according to the reaction below, which has a sodium carbonate reacting with 2 nitric acids to give us 2 sodium nitrates, a carbon dioxide, and water. Okay? So in this problem, we are asked volume of the 0.150 molar nitric acid solution. And we're given a volume and a molarity of a sodium carbonate solution. So I've got volume and molarity, and I've got molarity and I'm asked volume. I'm going from volume to volume. So we're using the top line here. Okay? So if we break this down and look at what we're given that we have 35.7 milliliters of our sodium carbonate solution. And the molarity is given to us as 0.108 molar. Okay? So my step one is to go from milliliters to liters. Now I'm just going to do this quickie, 35.7 milliliters, 1 liter for every 1,000 milliliters, so that's 0.0357 liters. So now if I look at this, I'm going to follow my bouncy ball pattern. I'm going to go volume of A. In this case, A is my sodium carbonate solution. And then I'm going to go to moles of sodium carbonate. And then I'm going to go moles of nitric acid. And then I'm going to go volume. Now when I do this, I'm going to get a volume in liters. So I'm going to start with the 0.0357 liters sodium carbonate. Now this first step uses the molarity of my sodium carbonate solution, which is right here. I have 0.108 moles of sodium carbonate for every 1 liter of solution. So liters and liters divide out. Following our pattern, the next thing we need to do is we need to go from moles of sodium carbonate to moles of nitric acid. Well, the relationship here is 1 mole of sodium carbonate for every 2 moles of nitric acid. I got that from the balanced chemical equation. So 2 moles of nitric acid, 1 mole sodium carbonate. So notice the moles and moles of sodium carbonate divide out. Now I'm in 2 moles, I'm in moles of nitric acid. Our last step is to go from moles of the nitric acid to volume of nitric acid solution. Okay? Now we've got the molarity of nitric acid. Now I want to think about this for a second. Molarity is a ratio between moles of solute and volume of solution. When I write 0.150 molar, what I'm saying is that I have 0.150 moles of nitric acid